Household electricity is usually treated as something stable and continuous. In most daily situations, it arrives through a fixed system that rarely needs attention from a user. You flip a switch, and power is present. Behind that simple action sits a layered structure that includes generation plants, transmission lines, regional distribution networks, and local service providers. Each layer depends on the one before it. This structure works as long as all parts remain aligned. Electricity is generated in large facilities, moved across long distances through high-voltage infrastructure, then stepped down and distributed into residential areas. From there, it passes through local grids and finally into individual homes. At the household level, the system feels invisible because most of the complexity is handled upstream. When any part of this chain is interrupted, the effects move downward. A disruption in generation, maintenance in transmission systems, or strain in distribution networks can reduce availability or create temporary instability. Even localized issues, such as overloaded circuits or weather-related damage, can affect supply at the residential level. In those moments, the system shifts from predictable delivery to constrained or inconsistent output. At that point, the dependency becomes more visible. Households that rely entirely on grid supply experience direct limitations in heating, cooling, communication, refrigeration, and general electrical use. The structure that normally functions in the background becomes a central constraint when it is no longer stable. Because of this, different categories of solutions have developed around the idea of reducing reliance on a single centralized source. These solutions are not all structured in the same way, but they generally fall into a few broad system types. One category is backup storage systems. These typically involve pre-stored electrical energy held in batteries. The structure is simple. Energy is collected from the grid or another source, stored in a chemical medium, and then discharged when needed. The strength of this approach is its immediate availability. When the main supply stops, stored energy can be accessed without delay. The limitation is that storage is finite and must be replenished through the same external system it is meant to supplement. Another category is external fuel-based generation systems. These rely on converting fuel into electrical energy through combustion or mechanical rotation. Structurally, they create electricity on demand rather than storing it. This reduces reliance on pre-charged reserves, but introduces dependency on fuel supply chains and maintenance cycles. They also tend to operate as isolated units rather than integrated household systems. A third category is renewable capture systems. These include configurations that convert environmental inputs such as sunlight or wind into electrical output. The structure here is based on continuous input conversion rather than storage or combustion. These systems can reduce dependence on external supply chains, but they are typically variable, depending on environmental conditions, and often require storage or supplementary systems to stabilize output. Each of these categories addresses the same underlying structure, reliance on a centralized grid. However, they do so by shifting where energy is sourced, how it is stored, or how it is generated. None of them completely removes dependency on external systems, but each one changes the shape of that dependency. Within this broader landscape, there is also a format that is often presented in a different way. It is not defined by a single manufactured system, but rather by a build-from-plan structure. In this format, the focus is on documentation that describes how a small-scale electrical generation setup can be assembled using specified components. Instead of a finished, sealed device, the structure is presented as a set of instructions. These typically include a materials list, a layout of component arrangement, and a step-by-step assembly sequence. Some versions also include wiring diagrams or power flow explanations, showing how energy moves through the system from input to output. The goal of this format is not to provide a pre-built unit, but to describe a repeatable construction method. At a functional level, the process begins with sourcing individual components. These may include mechanical parts, electrical connectors, and structural housing elements. The next step is arrangement, where components are placed in a defined configuration based on the provided layout. After that comes connection, where electrical pathways are established according to the diagram. Finally, the system is tested at a basic operational level to confirm that the structure behaves as described in the documentation. What distinguishes this format from traditional solutions is its structure of access. Instead of acquiring a complete system, the user follows a procedural map. The system exists as instructions before it exists as a physical object. This shifts the dependency from purchasing a finished product to following a defined construction process. In practical terms, this type of format is usually discussed in relation to household-scale applications. The intended scope is not industrial output, but localized electrical support for basic use cases. The emphasis is on repeatable assembly and adaptation using commonly available components rather than specialized manufacturing. This kind of structure may be relevant for situations where individuals are looking at reducing direct reliance on continuous external supply. It does not remove the existing infrastructure, and it does not replace the primary electrical grid. Instead, it adds an additional layer that can operate alongside it, depending on how it is configured and implemented. In some cases, it functions as a parallel system. In other cases, it operates as a supplementary source that activates only under specific conditions. The role it plays depends on how the system is designed at the structural level and how it is integrated into household use patterns. From a dependency perspective, the key shift is in access. Instead of relying entirely on a single external provider, the user introduces a secondary structure that can operate independently within defined limits. This reduces the number of steps between energy need and energy availability, especially in scenarios where the primary system is interrupted or constrained. This is why these build-from-plan systems are often documented in step-by-step guides. The purpose of those guides is to map the full structure from components to operation in a linear format that can be followed without requiring interpretation of complex engineering design at every stage. They typically present the build as a sequence rather than an open-ended design problem. In many discussions of off-grid or reduced dependency systems, references are made to structured documentation that outlines these builds in full detail. These references usually appear alongside explanatory material that describes how the system is assembled and how it fits into broader household energy planning. For viewers exploring this topic further, it is common for one such structured reference to be included in the description of related videos, especially where the focus is on step-by-step implementation formats rather than conceptual overviews.